Good morning,
Good
Juan.
morning.
How are you?
Okay,
Okay.
I'm okay. Yes, considering the situation, really, I'm extremely worried about what's happening in this country. Extremely.
In Israel.
More than last week. This week is the worst.
I wish we could talk about it, but
Yeah,
we are
let's go move on
inside a
to
deep
better
learning
things.
course for mathematicians. So let's continue. Last time we finished preparing our data. Let's. I will share my screen now, and we'll look at what we did last time. Okay, this is not relevant. You do see my screen, right?
Yes.
Okay. Let's see. This is what you. There is a link in the YouTube, in our last lesson YouTube video to this notebook here. Let's make some space. Now I will run all the cells at once in order for everything to be. Let's do it in two steps. First, let's clear all the output from last time. So edit, I think, clear all outputs. And let's have a look. We have a table of content here. So we are dealing with, we finished dealing with the data set, loading the data set, and now we're going to start training. So now I will run all the cells at once. Run all, I will say. You see everything is running now. Let's see.
Where is it running? On your computer? No.
Actually, it's not running on my computer. It's running on a virtual machine on Google's farm. That's why I didn't need to install anything. Everything is doing remotely. I'm doing everything remotely.
And they're so generous that they let everybody run on their
generosity is relative terms. They give us some resources for free, yes. They even give us some GPU here. You know what GPU means?
No.
A CPU is a central processing unit. It's like a little computer. And GPU is a graphical processing unit. And for machine learning, we use lots of matrix multiplication and lots of parallelism. So in order for things to run much faster, we use GPUs. The same hardware that use gamers for graphics.
Okay.
And they are kind enough to give us some in order to accelerate our computations. And where were we? Let's see. And so just a reminder, this is downloading the dataset from the internet. This is unzipping it, like uncompressing it. We have all the files here. This is using some image library to load the images. We've been all through that. Nothing new here. This is the ugly cat we've seen last time. Load data sets. That's what we've programmed last time. Just a quick reminder. Let's see. This is the main thing we did last time. We wrote a function named load dataset, which runs through all the files and loads them. This is the loading of an image. This is converting it to a tensor. Remember, this is flattening it. Remember how we managed to know how to flatten an image? We asked ChatGPT.
More or less remember, yes, okay.
Yeah. Everything should be working now because I've already run all the cells. DS is the name I gave to the data structure. And do you understand this line here? What it means?
No, what is F? F is the vector? No.
F is a formatted string. Let me explain it because I think we didn't talk about it. I could do a print, oh, sorry, just a minute. Print hi, right? This should be working, right? Hi. And suppose I have a variable a which equals 17, and I want to print its value. If I will put a here, I will just get high a, right? But I want the value of a. So in order to do that, I declare this string as a formatted string, and I put this a inside a curly bracket like that. You see, this is the way to format a string and to plant, to embed.
Okay, what does the F
variable
mean?
inside.
Whoa. What is F? F is find the
No, F
value
is
of things?
just a notion of a formatted string. It's just marking this string as a formatted string. You put it just before the string, and it means this is not just a regular string. It's a string which is made of. It is formatted of variables that are planted inside.
Okay.
So you see, this 17 was planted here.
Yeah, nice trick. So it gives you flexibility, yes.
It's just a convenience way of printing stuff.
Yes.
So let's go back to this line. So print formatted string. What did I plant inside? Len of ds. You remember what len means?
No, length, what is it?
Yeah,
No.
it's a shortcut for length. And ds is our data set. What is this data set composed of? Do you remember?
I remember the three-dimensional tensor, 200 by 200 by 3. Okay.
Yes. Yeah, but the data set is composed only from pairs of xy,
Yeah.
many
Right.
xy. Each x is a flattened vector of an image, which was a tensor, and each y means what?
Value. Cat or dog. Yeah.
I'm sorry?
Y is a vector, which is either 0, 1 or 1, 0 or
Exactly.
infinity.
It's the labeling and the two-dimensional vector that indicates whether it's a dog or a cat.
But it's a probabilistic vector or not. It's
Yeah,
1, 0 or
yeah, it's a deterministic probability.
okay, so 1, 0, okay.
Yeah. So what did I say here? Len of ds is the number of xy pairs that I have.
Okay.
And it says I have 200 because
200 cats, yes, okay.
we had 200 images. And what did I write here? ds, what's that? Let's see. ds, let's do it in like in steps. First, we'll ask what's DSF0 means. Do you know what that should be?
Data set 0, that's the first dog, the first image or something like that. I don't
That's
know.
the first pair.
The first pair, yes.
White. Let's see. It's a pair.
Mhm.
The first element is a very long vector. This is why we have 3 dots here. And the second element is just a very simple vector, this one.
Mhm.
Okay. And if I want only the second element of this first pair, I can do this. This is the second element
Yeah.
of the first pair. Okay? And what will that will give me?
First, sorry, the first element of the second pair? No, no, no.
No, the
No,
second
it's the second element of the
first
first
pair.
pair. The second element, I thought it was the 0, 1 vectors.
Yeah, exactly. Let's see. Yeah, this vector. And if I will ask it for its shape, you remember what shape means?
Shape is the dimensions. What do you mean?
Right, exactly. That's the dimension. So it's 2 by 1 because it's a vertical vector.
Okay, yes.
Okay, so that's exactly what I printed here. It told me that we have 200 pairs,
Mhm.
and the shape of the label is 2 by 1.
Yes, okay.
It's just a printing.
So this you wrote or you asked him to write?
I wrote
You
this line of
asked him to
code,
write that.
the
Yes.
printing, and he printed it.
Yes, okay.
Let's run it again. I will get the same answer.
Mhm.
I will delete this cell because we were just playing here, right?
Okay.
Now we start the training process. So what is the training process? It's the gradient descent we were discussing earlier in this course. Okay? Let's see what I did here. Do you understand what I did here?
Sorry, you're asking something?
Yeah, I was asking if you understand this line here.
Yeah, yes, we did it a minute ago, yes.
Not exactly. It's the first element of the first pair, which is the
The
x,
first
right?
element of the first pair, yes, right.
Yes. So you understand why it's 120,000?
Yes, it's a vector of this length, 200 by 200 by 3.
Yeah, it's
Yes.
the flattened. It's a flattened
Yes.
tensor, which used to have
Mhm,
3
yeah.
channels of colors,
Uh-huh.
and 200 by 200, which is 40,000.
Yes.
Okay, I will delete that. We don't need it.
Okay.
What do you understand these 2 lines?
Print them. What is x dimension? X is the first dimension? Yeah. No. What is this x doing there? That's just because you asked him to write these words, okay?
Let's start
So
from the first line here.
yes, okay.
What did this line mean?
This line is 1 minute. What does the shape do there? What is the dot? I don't understand the dot there.
Dot belongs to. So let's go from left to right. DS is our data set, right?
Hmm?
DS0 is the first pair, right?
First element, and the first element in that, it's a vector. And
this is the X element, right?
yes, so this
And
first vector, the first element is a vector of
it's a flattened image,
120,000.
right?
And yeah.
And
Okay.
shape is its dimension. We've seen that it's 120,000 by something, by nothing. So this is the first element. I didn't want I will write again what we used to have in the.
I just don't understand the dot. I still don't understand the dot.
The dot means belongs to.
Belongs to.
I will explain. So this is the shape of this. When you say dot, you mean you are referring to something that belongs to this object.
So
The
it
shape of
belongs
this
to
object.
the right belongs to the left, not the opposite.
Yes, we read from left to right. So we read the object, and we ask him for its dot, which belongs to it, the shape of it. That's the way to read it.
Okay.
That's the shape of the first x. Okay.
Yeah. I don't understand the comma there. What does the comma do?
Yeah, because it's a vector with it's not really a matrix, right? It's like how do you say menuvan in English?
Degenerate.
How?
Degenerate.
Degenerate?
Degenerate.
Degenerate matrix. It's just one line, right?
Yes.
So
Okay.
that's the way it represented. So if I will just ask for its first element, oh, sorry. You see, this is the number I was looking for. This will be my dimension of the x. I would just wanted,
Okay.
I wanted to extract this number.
Mm-hmm.
So I said n will be the dimension of x. And I just put this whole expression here, okay?
Okay.
And now I printed a formatted string, x dimension equals to the value of n.
Yeah.
Let's run it.
That's fine.
Dimension, x dimensions equal to this, okay? Now we have this variable, we're gonna be using it. Now, let's start programming, okay? Train. So train will get a data set as a parameter. Let's give it some more parameters. Like for instance, we're gonna give it epochs. Epochs means the number of times we're gonna go over the data. It will be, in our case, it will be the number of steps we will do gradient descent. And we'll give it a default value. Have we ever used default values in this course? I don't think so, right?
Don't remember, no.
Let me
Okay.
let me
So you
explain
always do 70 steps in the gradient method. Okay.
I want to explain separately what's a default value for a parameters of a function. Suppose you have a function named foo, just an artificial function, and a is its parameter, and its default value is 17, okay? And all this function does is print a, okay? You understand this code of foo?
No. Foo a equals 17. Before you did.
Yeah, this is I just marked the new things. If I didn't write this 17, it was very, very simple function, right?
Yeah, will it now print 17 or what will it print?
Let's see, I could do for 3, and it will print 3.
Okay.
But I can also call it without any value like that, and it will print 17. It's a default value for a, for the parameter.
Oh.
So what it actually means, if a was not given, give it the value 17.
Where did you declare that the default is 17? So DEF is not a definition, it's default. Okay.
Yes, DEF is the definition of a function. The function name is
it is
foo.
definition. Yeah.
A is the parameter, and I gave it a default value if it's not given by the user.
Okay.
Okay, this is the default value for a parameter in function. So I give epochs the number 17. The user can ask for any numbers of epochs, but if he doesn't ask for anything, I will give it 17, just my number.
Okay.
Let's use another parameter, which is LR, which stands for learning rates. You remember what learning rates means?
No, no.
Let's make a quick rewind on the algorithm. So let's see. Are you tired?
No, I told you, I'm this morning with
you
low
are concerned
spirits.
about the country.
Yeah.
Because
and about myself in the country. Yeah, okay.
This is the y-axis, so the labeling axis, and this is the axis, which stands for our images, right?
Mm-hmm.
And we have a cloud of dots, right? This is our data set, right?
Mm-hmm.
Our data set is pairs of x, y, right? And we are trying to fit a function, right? That's our goal, to fit a function. Right? This is what we're trying to do.
Mm-hmm.
And we have a notion of distance between a function and the set of dots, right? We were talking about this, right? This is the distance, right?
Mm-hmm.
Okay, and the gradient descent, on what space it is being done, do you remember? So
set of functions. No, there are parameters defining the function.
Exactly. So this is f of this f of with parameters w, right?
Mm-hmm.
We pick for good values for w in order to fit the function, and our gradient descent will be on this w, right?
Yes, the set of parameters.
So we define a new function which is a loss of w, right?
Yes.
For each w, there is a distance between the function and the cloud, and we try to minimize it, right?
Mm-hmm.
So this is loss of w, a totally new function, and in order to visualize it, we were talking about topographic maps, remember?
Mm-hmm.
So we had contours, right? So this is a part of W. This is also part of W. And the loss is this X here, right? This is loss. Are you with me on that?
Yes. Just in the cats and dogs example, the function was almost linear, and then some.
Okay, the function itself for the softmax of a linear function.
Softmax of a
It's
function.
f of W.
And you're looking for the coefficients.
I will write it just a minute. This is f of W, which gets an x, right?
Mm-hmm.
And it was defined as the definition of this function is actually called the architecture of the neural network. Mm-hmm. But we didn't talk about neurons. We talked about functions. Softmax of W, which is a matrix, in the dimension of W was 2 on n, multiply, this is a matrix multiplication of X. X is a vector. So this was our function. For every W, a set of parameters, we have a function. Remember what softmax means?
Yes, more or less, it is e to the exponentiation.
Exactly, and normalized.
Yes.
For it to be a probability, right?
Yes.
Okay, so we now do gradient descent on the space of W, and we try to minimize.
For every x, each of your examples.
No, X is not a player here. We have a cloud of points, and for every W,
Yeah, you sum the loss is the sum over distances, right?
It's actually the average of it. Yeah, you can say the sum.
Okay.
Yeah.
Yes.
So on this space, we are trying to find the minimum, right? By doing gradient descent, right?
Yes, yes. Okay.
So what do we need to do in order to do gradient descent? We always have to know the gradient, which is the partial derivatives of the loss in respect to a weight, right?
Yes.
So we were talking about this value, partial derivatives of loss to a specific weight. We have many of those, right? We call it Wij.
Yes. Okay.
Suppose this is known. Let's call it Dwi. What are we going to do with it? If we had it.
We're going to go in this direction, or actually minus this.
Exactly. We want to go in this direction, but not all the way, remember?
Yeah, that's the restricted learning. Okay.
That's the learning rates. So
learning rates, yeah, okay. You don't want to jump too far. You're going, but this is some parameter that
exactly. So
depends or something.
Let's write it down. So the update rule was this: the new weight will be the old weight, the same weight.
Plus some number theta times this minus. Minus the gradient.
Minus because we're going to the opposite direction of the gradient. Let's call this number learning rate, okay, LR. This is LR multiplied by what?
By the gradient, okay.
Yeah, by the partial derivatives, yes.
Okay, that's fine.
Okay, this is the update rule. So we have everything we need, we can start programming.
So I now remember that are, and this is, it looks so primitive, sorry to say. Do you believe that after we program it, it will really discern cats from dogs?
I agree that it looks primitive because gradient descent, it's the most primitive optimization algorithm you can come up with.
Yes.
It's very, very primitive, and it's kind of a miracle that it's enough to work. But you should remember that we are dealing with a very, very high dimension, and we don't have good intuition of what's going on there. But you're right, it's very, very simple.
And now I'm wondering, will at the end of this series of lectures, you're going to have a program that discerns between cats and dogs?
My intention is that it will work, that it will be able to distinguish between a dog and a cat, but I'm not sure it will work with, this small data set. I might need some more. I will, but the most important thing is the idea. Yeah. The idea is working. Maybe we won't have enough, details that makes it work, but we'll see. I hope it will work as it is. Also, I hope I made my derivation right? It's kind of complicated, you see?
Yeah.
And you were not willing to check it.
No, I'm not willing to read this.
Okay.
I
Maybe someone else will. Okay.
He once tried to sell our kid to his grandmother, and she said, I raised my children. I don't owe the world anymore.
But you realize, Vaughn, that even the smallest bug here can cause our program not to work.
Of course, yes.
Okay. By the way, we can do other things. Instead of doing, this is a symbolic derivation. We can do a numerical derivation. Do you know how we can do that?
No,
We can make
the definition of the derivative, yeah. So
exactly, we'll just use the small epsilon,
yes.
and we'll see the effect, and we'll just divide it. So that will be our way to see if this symbolic calculation is correct. So I don't need you, actually. I have the computer to check me.
Good. Okay.
Okay, so let's start programming now. Train data set, the learning rate, let's give it a default value of just a minute.
1/1000.
I will use like something like that. This is the 1/1000. Yeah?
Okay.
1/1000. This is the initialization of the weight matrix. What did I do here? This is the, I just use the normal distribution for giving the weight matrix initial values. So NP is, you remember what NP means?
No, I knew it once.
It's just our NumPy, our numerical library that we use for matrices. Random, it is a model that is responsible for generating random numbers. Normal is the name for normal distribution. And I ask it to have a mean of 0, standard deviation of 1. And this is the dimension of the matrix. Yn by 2, you know?
Dimension of the outcome matrix?
Pardon?
No, sorry. N was 120,000. Yes.
Why is it 2 by n, the matrix? Let's just make it short. This is our f, right? F's receive, what is x? X is a vector, which is a flatten of an image, right?
Yes.
And n, its dimension, it's 120,000, right? So I'm going to multiply it by a matrix. What should be the dimension of this matrix here that I'm multiplying it by? So
120 by 2, yes, of course.
Yeah, so this is 120.
2 by 120.
Yeah, why 2?
Why 2? Because you want a vector at the end.
Yeah, at the end I want a
two-dimensional
vector,
two-dimensional
right?
vector.
Yeah, so this is
cats and dogs. Yes, okay.
Yeah, cat and dog, exactly. Okay, so that's why when I initialize the weights, I chose this dimension. But you know, what's the importance of the way I initialize this matrix? In terms of gradient descent, it's actually the point that I'm starting my gradient descent from, right? So from one point, it might converge. From another point, it might not converge. So this is the whole issue that I can play with. If it's not working, I can start from many different points, but I hope it will work as it is. Okay?
Yeah.
You understand that I'm just decided where I'm going to start my gradient descent. Okay. Okay, so now I will make a loop on the epochs, like 70 epochs. So 4 epoch in range epochs. So epoch will be 0, 1 until 69. Okay? It's just a loop on indexes. Remember range? Range is number from 0 to 69 now.
Yes, or 4 in the Fortran or.
Yeah, 4 is the indication for a loop. Now what I need to do, I want to do gradient descent, so I need to calculate the gradient. So let's call a function that we haven't written yet, but we will. Let's call it calculate gradient. I didn't write it, but I will. What I'm doing now in computer programming is called a top-down design. I'm calling a function that I didn't write yet, but it's a good practice because this way I will know exactly which function to write, okay?
Yeah.
Okay, so calc gradient should get the data set. It should know all the points, right? And what else? Let's see, when I calculate the loss of the W, it needs to know current W. What else does it needs to know? I think that's it. Everything else, I think it will be enough. Okay, so now we have DW. It's a matrix of the same size as W, but in each entry, it will have the partial derivatives. It makes sense?
Yes.
Okay, now I need to do my update rule, right? Let's do it matrix-wise.
Sorry?
What?
W is W minus
W
DW.
equals W. You remember this
LR.
equals is an assignment, yeah.
Yes, yes. W minus LR times DW. Okay.
Exactly. Well done. So this is exactly the update rate, the update step. We could have written it in a shorter form like that. Do you know this form like that? Have you ever seen it?
No, I've never seen it.
So let me show it to you. It's very useful. Just a minute. Suppose I have A equals 17.
Okay.
Oops, 17. And I do A plus equals 3. And I will ask to print A.
That's 20.
Yeah, it's 20. And
A
minus,
plus.
it will be 14. And also I can do multiplied by 3.
Okay.
I can also divide by 3.
Okay.
It's just a shortcut, okay? So is this update rule clear? I think it is.
Yes, okay.
Okay, now what else do we need to do? I want to print the process of training will take some time, and I want the user that will run the training to see the progress. So after every certain number of epochs, I want to print something. So let's add another parameter here, which we'll call it display period. It will be, oops, just a minute. This period will do something like that. If epoch, this is the number of epoch we're at, modulo, this is modulo, this period. So if this period will be 2, every 2 epochs, it will print something. Well, we'll call a function named display train status. You understand what I'm doing?
Where was definition train to term? Status is the current one. Okay.
You remember this is the sign for modulo?
Modulo, yes. If epoch to the
epoch is the number of iteration we are currently at.
So if it is 1, if epoch
let's give this period a default value of 10, for example.
Okay, so every 10 steps. Okay.
Every 10 steps, it will display train status.
Okay. But display in what sense? Displaying will give you the long vector W, 120,000 vector.
This is not very useful for a human being to see, right?
No.
What will be useful for a human being to see? Maybe the value of the loss, right? I will want to see that the loss is coming down.
Okay.
So let's compute the loss here. Let's write loss equals, we'll call another function calc loss. What does it need to have? It should have the data set and W. Maybe that's it, loss. And let's send loss to this function. I think that's enough for train, right?
Okay.
But now we need to implement calc gradient, calc loss, display. We need to implement 3 functions, right? I think it will be a good time to stop now. What do you think?
Yeah. Definitely.
You are always.
My head is not completely there. Just because I read the newspaper this morning.
Okay, fine. You can continue worrying about your country.
Okay, and you about yours.
Actually, I'm worried like you are. Okay, and I'm gonna see you next time.
Okay. See you.
Thank you.
Bye-bye.
Bye-bye.